This is section 12.7 from our textbook. You should read through this on your own. I'm going to point out a couple of things in this video. In section 12.7, we are using normal and tangential components. The equations for this section are in the fourth line on your equation sheet. So first of all, if you look at the equation for position, remembering that the u hats are for unit vectors, you see that the position is 0. This is because the origin is located at the location of the particle and it moves with the particle, so the particle's always at the origin, so the position vector is always 0. We have a velocity vector here, and we only have velocity in the tangential direction. It's called the tangential direction because it points in the direction that is tangent to the path, and also it points in the direction that the particle is going in. So if you look at our equation here, v would always have to be positive because the particle is always going in the tangential direction. We have an equation for acceleration here, which, well, let's talk about it now. So v dot, that would be the derivative of the speed. And if you think back to physics 161, when we did circular motion, the speed can change. If the particle is going around a circle, it can be speeding up or slowing down. That's what the v dot is telling you. But if you're going in a circle at a constant speed, you can still have acceleration. It would be directed inward towards the center of the circle, and that's what this v squared over rho is here. In physics 161, we call that v squared over r, and that was the centripetal acceleration. And so rho becomes r when the particle is moving in a circle, but for the motion that we're looking at here, the particle doesn't have to be moving in a circle. So in general, this is how you find rho. Rho is the radius of curvature that they talk about on page 56 in the textbook. For most of the equations, probably all of the equations on the equation sheet except for the one for rho, they're either easy to remember or you've seen them before and should be familiar with them, except for rho here. It's not like it's that difficult to remember, but I don't really think it's worth memorizing because you only use it in this case. So that's why this is on your equation sheet. And then we have equation 1219. If you remember when we talked about equation 12.3, I said something about this should really be a dot product. So you kind of see that here because it's not all of the acceleration, it's just the tangential component of the acceleration, which would be v dot. We know that because if you look at equation 1218, it's the tangential component going in the tangential direction. That's what the unit vector u hat sub t is for. So whatever's in front of that unit vector for the tangential direction would be the tangential component of the acceleration. So that's v dot. Okay, so those are the equations that we have for this section. You should read through the first 4 pages of this section on your own. There are a few other points that I want to make there. First of all, this handout here for equation 12.7 is on the M drive in the Notes and Examples folder in my course folder for ENR 252. So if you do want to take a look at that, that's there. Okay, so a couple things that I need to go back over. So the particle is moving in the tangential direction, and the tangential direction is tangent to the path at the current location of the particle. The normal direction is pointing inwards. Now, you don't always have something circular, but you can approximate a small portion of the path as part of a circle. That would be the ds would be the arc length of the circle. And then you can find the radius of curvature, which if it was part of a whole circle, that would be the radius of the circle. And you can find that using the equation here. Okay, so if you take a small enough piece, you can treat the small segment ds as part, well, the arc length for part of a circle, except that it doesn't work if the object is going in a straight line. So if you are looking for the normal direction and the object is going in a straight line, I said the normal direction points inward, but there is no inward if the object is moving in a straight line. But if you look at the definition for the radius of curvature, you can see what happens if the object is moving in a straight line. You can see what happens using the definition for the radius of curvature. Or you could just think about it. If you make, as you make the radius of your circle bigger and bigger, this arc length here is going to become flatter and flatter. You can think about the surface of the Earth. The Earth is a circle, but you can't really tell if you look at a small piece of the surface of the Earth. So as that radius gets larger and larger, ds becomes flatter and flatter. So if the object is moving in a straight line, then the radius of curvature is going to, well, it is infinity. That means that when you look at the acceleration, because you have the radius of curvature in the denominator, and that's going to infinity, the normal component for the acceleration is 0, and you don't have a normal component for the velocity because the tangential direction is the direction that the object is going in, so all of that speed is going to be in the tangential direction. And as is usually the case for a coordinate system, the tangential direction is going to be perpendicular to the normal direction. That's only 2 dimensions, which is all we're going to use here, but there is a third direction, and that's the binormal direction, and that has to be perpendicular to the tangential direction and the normal direction, but that leaves you with 2 choices. So here it could either be pointing up like this, or it could be pointing in the opposite direction. So to find the binormal direction, you can use the cross product here. Okay, now something interesting happens when we look at the acceleration. So first of all, remember that for the position, the object is always at the origin, so the position of the object is always 0. And then for the velocity, the magnitude of the velocity is just v, the speed. You could call it the derivative of the speed, or the derivative of s, where s was our position back somewhere here. We used s for position. There we go. So the derivative of s with respect to time, the derivative of s with respect to time, that gives you v. So s dot is v, that's going in the tangential direction. But then when we look for the acceleration, we're supposed to take the derivative of the velocity with respect to time to get the acceleration. But you cannot just take, let me see if they do this here. Okay, so you cannot just say the acceleration is v dot time in the tangential direction, because you're taking the derivative of this whole thing, and you have to take the derivative of the v, but also the derivative of the unit vector. This is kind of related to what I just talked about that we looked at in Physics 161. If the object's going in a circle at a constant speed, it still has acceleration, even though it's moving at a constant speed, just because the direction is changing. So it's something similar here, because the direction of the tangential vector is changing. When you take a time derivative, you also have to take the time derivative of the unit vector that you have here. So this is taking a time derivative using the product rule. Okay, you can read through what they have here to see how you find the acceleration then. I'm going to look at it a slightly different way. So if you look at the handout for section 12.7, that's on the M drive, which you really don't need to do, but it's there if you want it. What I do here is similar to what they do in the book, but I think there's a better way to take the derivative of unit vectors, so we're going to look at that now, and this is also on the M drive. So if I have a unit vector, I know that the magnitude of a unit vector has to be equal to 1. It can be pointing in any direction. We're going to limit ourselves to 2 dimensions here, but it can be pointing in any direction, but it has to have a magnitude of 1. This means that any unit vector that I have that's in the xy plane, I can write it like this. I choose some angle, and it's cosine theta I hat plus sine theta j hat. Now, I hat and j hat are really nice unit vectors to work with here because I hat is always pointing in the positive x direction, and j hat is always pointing in the positive y direction. So when I take a time derivative for I hat and j hat, I'm always going to get 0 because the direction of those unit vectors do not change, unlike the unit vectors for the normal and tangential direction, which are going to change as the object moves along the path. Okay, so here we have an example of that. So this is the unit vector pointing in the tangential direction when the object is at this point here. And sometime later, see how that unit vector is now pointing in a slightly different direction. And same thing with the unit vector pointing in the normal direction. The direction has changed slightly. We don't have to worry about that when we use I hat and j hat. Okay, I'm going to skip over what I have here. But so now we have our unit vector here. I take a time derivative of it. I take a derivative of cosine theta, and I get negative sine theta, but that's taking the derivative with respect to theta. I need to take the derivative with respect to time, so that I have to multiply by d theta dt, which is theta dot. Similarly, when I take the derivative of sine theta with respect to time, taking the derivative of sine theta with respect to theta gives me cosine theta, then I have to multiply by theta dot. If you compare cosine theta plus sine theta to minus sine theta plus cosine theta, if this angle here is theta, cosine theta I hat plus sine theta j hat is pointing this way. If we assume our angle is somewhere between 0 and 90 degrees, then this vector would be in the first quadrant. If your vector is between 0 and 90, then minus sine theta plus cosine theta j hat, that's going to be a negative x component and a positive y component, so that is in the second quadrant. And these two vectors are perpendicular to each other. So whenever you take the derivative of a unit vector, what you get is always perpendicular to the original vector. Okay, so if you know it's going to be perpendicular, and if we're working in 2 dimensions, that only leaves you with 2 choices. It could either be perpendicular and pointing this way, or it could be perpendicular and pointing the other way. So we have minus sine theta I hat plus cosine theta j hat times theta dot, which when I said this was pointing in the second quadrant, I kind of forgot about the theta dot. So if the theta dot is positive, it's still pointing, well, it's still in the second quadrant, but if theta dot is negative, then it's pointing 180 degrees in the opposite direction, this way. Okay, so that should help you understand what's going on here. You should understand how they arrive at the result, but you're not going to need to know how to do this on your own. So as long as you can read through the derivation here and understand what they are doing, that's all that I expect from you. I'm not going to ask you to reproduce something like this on an exam. Okay, so you can read through page 56, 57, 58, and 59. When they give you a green box like this on page 59, it's a good idea to pay very good attention to what is in the green box. Those are nice summaries of what is in this section, but you should still read through the other 3 pages.